Hello, so today's section is on solving exponential equations. So before we jump into actually solving equations, we're first just going to look at how to rewrite things with a common base. So first we're just going to rewrite each of the following with base 3. So first we have 27. 27, you could actually rewrite it as 3 times 3 times 3. So that basically is base 3 to the power of 3. So that's one way of writing it. Okay. All right, on to the next one. So 9 to the power of 2. Now 9, I'm sure you know, could be written as 3 to the power of 2. And this whole thing is to the power of 2. And when you have an exponent to an exponent, you'll need to multiply that. So these two here, you'll have to multiply it. So it'll be 3 to the 4. And to the third one here, now this one looks a bit more complex. So we'll need to rewrite a couple of things here. Now 27, we already know from part A, 27 could just be written as 3 to the power of 3. And this whole thing is to 1/3. Okay, and 81 is 3 to the power of 4. Now, root 3, this part right here, root 3 is also known as 1/3. And this whole thing is to the power of 2. Okay, so therefore, again, exponents, you're just going to be multiplying it out. So 3 times 1/3 is just 1. So we just have 3. And then 3, and then we basically have 4 times 1/3 times 2. And I guess here there's actually a 1. Okay, so we basically have 3 and then 1, or equals to 3 times 3, and then we have basically 8/3. And this would equal to, now we need to add these two together, so we 3, 1 plus 8/3. And 1 is basically just 3/3 plus 8/3. So that'll equal to 3 11/3. Well, another way you may have looked at this was, just call it, remember when you have something to the power of 1 over, that basically just means you have a root, right? So you could think of this as cube root 27 times your cube root 81 to the power of 2. Now we know cube root 27 because we know 27 equals to 3 times 3 times 3. So if you cube root it, that basically just brings you down to 3. As for the cube root 81, well, we'll just follow what we did with our first solution on the left here. So we know it's still 3 to the 4 times 1/3 times 2. And it basically brings us back to this step that we had here, okay? So, and ultimately that will also bring us to 3 11/3. So both ways can work. However you want to simplify it, it is okay, as long as you're still working with base 3. All right, so now that we've got a hang of writing things with the same base, we're actually going to start doing our equations now. So solve each equation. So our first one here, like the first thing we need to do is we need to write terms with the same base. So things need to have the same base before we can actually compare them. Now, in terms of this case, our base right now is 8 and 16, and those could be rewritten with base 2. Because 8 is basically 2 to the power of 3, and 16 is basically 2 to the power of 4. So if we rewrite that, 2 to the power of 3 times x minus 1 equals to 2 to the power of 4 x minus 3. Again, exponents to the exponent, you'll multiply them. So we have 2, 3x minus 3 equals to 2, 4x minus 12. Now, since these two terms have the same base, then the exponents must be the same, or else you're working with two different things. So our term 2, since the bases are the same, we can basically ignore the base now and just solve with just exponents. So removing the base, we're left with 3x minus 3 equals to 4x minus 12. And now it's just a matter of solving for x. So with algebra, I'm going to move all the x's to the right and the numbers to the left. So we have negative 3 plus 12 and 4x minus 3x. And here we're left with 9 and x. So x must equal to 9. Okay, so let's look at our second example now. So this time we have 27 and 81. Now, what can be the common base for these two terms? If you think back a couple examples ago, both of these could have the base 3. So let's write that. So 27, if you remember, is 3 to the 3, x minus 2. And 81, is going to be 3 to the 4. And it's x plus 3. Now, when we have something that is 1 over, or the reciprocal, that is also to the negative 1. So for example, if you remember, x to the power of negative 1 is equal to 1 over x, right? So we can just rewrite this term on the right here with another exponent. So let's rewrite that. So 3 to the 3 x minus 2 is equal to 3 to the 4 x plus 3, and all of this to the negative 1 because it's 1 over. Now, we're just going to do the same thing. We do have the same base. Let's just write it out. Let's just multiply it out. So 3 to 3x minus 6 equals to, I was going to break it up into two steps here. So 3, well, when we have 4 times negative 1, so that's negative 4. So negative 4 times x is negative 4x. Negative 4 times 3 is negative 12. Since we have the same base, again, we could just ignore the base and just compare the exponents. So that leaves us with 3x minus 6 equals to negative 4x minus 12. We'll have all the x's on one side. So this time I'm going to move the negative 4x to the left. So 3x plus 4x equals to negative 12 plus 6. So we have 7x equals to negative 6. X equals to negative 6 over 7. Okay, And our third example here. So this one is a little different. It looks a little bit more complex than the other ones. But I'm just gonna write out something here and then you may be enlightened by what you see. So I'm just gonna say assume a equals to 3x. So if I replace 3x with a, then that means the first term I'm just left with a squared minus 10a plus 9 equals to 0. Oh, that looks like another one of those factoring scenarios again. So I'm just going to factor it out. So we have a 9, 1 minus minus. Okay, and now I'm just going to put my terms back in. Oh, and all of this equals to 0. So we have 3x minus 9, 3x minus 1 equals to 0. So that means we know our first term, 3x minus 9 must equal to 0. Oh, actually, let me just put it a little further up. The smaller arrow. So we know 3x minus 9 equals to 0. So 3x equals to 9. My first scenario, x must equal to 2. And with my second scenario, we know 3x minus 1 equals to 0. So that means 3x equals to 1. Well, x equals to 0. So we have actually two possible solutions here. It could be 2, could be 0. Okay. So right now we've just solved it algebraically. So another way to solve, well, is actually just by using, or graphically. So yes, you can use your graphing calculator graphically or Desmos. Okay, so that is the second way in which you can find a solution. All right, so let's just end it off by looking at a word problem and how we could build this. So how long will it take a $5,000 investment to be worth $6,000 at 6.6% interest? Now remember, this 6.6% interest is an annual thing. Even if it's not, written out as annual, that's what it means when it comes to interest, okay? So we'll first start kind of by sketching out a graph. So we know it starts at 5,000. And since it's an investment, the money will be going up. So it's going to go up something like that. And we're kind of looking at, well, when is it going to be at 6,000? So something like that. So this is how this equation will be built. So we have our 5,000. And we do know we want to get to 6,000. That's our kind of final amount. And when it comes to interest, well, it needs to grow from 100%. So that's why there's 1. And the whole year, it will be 6.6% interest. So to put that into decimals, it's going to be 6, like that. But this is compounded monthly, okay? So monthly basically means 12 times in a year. So this number is actually going to be divided and added on 12 times. And how frequently does that happen? Well, that's going to be our exponent here. And that means it's going to, happen some t times. And if we say t represents a year, then that means it's going to happen once every month. So you'll need to divide that time into 12 separate pieces to represent monthly. So in this case, you'll just need to note that t in this case represents year. Okay. The 12 here is compound monthly. The 0.066 is just the interest, which we just mentioned. This is your initial, and here is your final. So now that we've built our equation, we'll just need to actually solve for it. And again, since we haven't learned about logarithms yet, currently you will have to go with the guess and test method. But we can still simplify it before you start plugging in numbers. So first we're just going to move the 5,000 over. So we have 6,000 over 5,000. Okay, and 1 plus this number here. Let me just punch that in. 1 plus 0.066 divided by 12. So that'll be 1.0055. And this number, t to the 12. So now you're just going to put in different numbers into t to see what number will bring you the closest to your fraction here. And so the closest time you should get to is about 2.8 years. And that is it for this section.